Hello AP Physics students, happy Tuesday. Welcome back to my little physics lecture series here. Today's actually the last day of new material in this unit. So this is the last day of new material in the magnetism unit. And then the rest of it is focused on working on some AP problems and then getting the progress check done by the end of the week. So this is the last new thing, and it's kind of a weird one. Really, what we've seen so far is we've seen Ampere's law, which helps us figure out the magnetic field of certain currents, but it's really limited because you need some symmetry, otherwise it's really hard to work with. But this thing today is called the Biot-Savart Law, and here it is. Biot-Savart Law. This will help you find the magnetic field of any kind of current, although we're really going to limit what we actually use it for. So let's take a look at what it is, and then we'll kind of break the pieces down and we'll see what happens. So the first thing is, let's state it. The magnetic field is going to be the integral of mu naught I over 4 pi r squared dl crossed into r hat. Now, the book or the equation sheet may actually have a slightly different version of this. But this is the one I like to use. It's the one that makes the most sense to me. And it is really intimidating. This equation just looks terrible. It's not as bad as it looks, but it does look just terrible. So let's break down what the pieces are, and then we'll take a few examples and we'll see what we can do with it. So first, mu naught. That's just the permeability of free space. That's a constant. That's just it. 4 and pi, those are also constants. So that is, that's no problem either. This is the current. This I is the current in the wire. So whatever current you happen to have flowing through there, that's it. This is going to be, the R is going to be the distance that the magnetic field, the position that the magnetic field that we're looking for is from that piece of current. And so that's it. This is how far this is to the point that we're interested in. Then dl, this is the piece of wire. It's a tiny little piece of wire, a little tiny piece, dl, just like we've talked about tiny little pieces so far. So this is related right to this, that the current and the little piece dl. What's nice about that is because we're really looking at dl, this really, because we're dealing with this makes this into a constant, essentially. We're not going to have to worry about that. So mu naught I over 4 pi, that is all constant stuff that comes there. And then we've got dl and r squared that we're going to take a look at. So we're integrating it over that point. Then the last part. This might look really foreign to you. This is a cross product, and this is r hat. R hat is a unit vector that points in the direction of r, but only has a length of 1. So this only has a length of 1. What this really does, because this is dl crossed into the radius vector, what this does is it essentially adds sine of theta to the whole thing. That's really the main aspect of what it does, is it adds sine of theta. So when you really break this down, it's not as intimidating as you might think, because mu naught I over 4 pi, those are all constants. They're all going to come right out of the equation. This is how far the length of wire is from the point we're interested in the magnetic field. This is us integrating the length of the wire. And then this is the sine of theta, because we know the way that magnetic fields work. We know that the magnetic field is going to be perpendicular to the wire because of our right-hand rule. So let's take a really simple example first. This example is the most common one that would ever show up in the AP test anyway. So we'll take a look at it, and then we'll see how it's not as bad as it looks. I will say I used to not, or I was considering not teaching this for a while. I thought, you know what, it really hasn't shown up in the AP test. I don't know how important it is. And I taught it for last year, and then it showed up on the AP test, and it was a problem. It's actually one of the problems you'll see that I recommend you study. So from that point on, we've been studying it, and at the same time, it's in every college course. So let's take a look at a really simple example, though. This is one you may have actually seen last year, but you didn't see why it happened. So here's the example. Let's say we have a current in a loop of wire going around like this. So in this case, it's going counterclockwise around some circular points. That's a wire of radius A. It's carrying current around, and I want to find the magnetic field right in the middle. Now you can actually use your right hand rule. You can point your thumb in the direction of the current, and then let your hand hit that middle point. No matter which position you go from, every single point is going to point up. So the magnetic field here is up. You can see it another way. If I cut this wire in half, if I cut it in half like this, then what you would have is a current coming out at you and a current going away from you, and this would be the radius A. So you can see in this case that if I look right in the middle, if I point my thumb up, curl my hand, it hits pointing up. Curl my hand around this way, it also points going up. But there's another right-hand rule, and it's the same one we use for the solenoid that can tell you this a little more quickly. Remember, you only need 2 right-hand rules, but this is a nice handy one. What you do is you grab the wire in the direction the current's flowing. So I grab it like this, and when I do that, the thumb points up. That's the way the magnetic field points. That's the north pole of this magnet, because this wire becomes a magnet that way. But let's see if we can analyze what it is, and we'll take a look at how the Biot-Savart Law looks, and it really doesn't boil out to be anything fancy at the end. So the Biot-Savart Law, again, is the integral of mu naught I over 4 pi r squared dl crossed into r hat. Okay, so here are the pieces. Mu naught's a constant, I is a constant, 4 pi are constants. The radius, how far is the wire from this point, is A. It doesn't matter where it is, every point on this wire is the same distance A from the current. So these are all constants here. So the first thing I do, I'll put that down. Magnetic field is mu naught I over 4 pi A squared. Now the next part I have here is the dl crossed into r hat. So crossed into r hat, let's do that part first. If we look at this, the question is, what direction does the wire make with the radius? So let's see. It's a little bit easier to see over here. The radius points in this direction, and the magnetic field points down. That makes a 90-degree angle. On the other side, the magnetic field points this direction, the magnetic field and the current points up. That again makes a 90-degree angle. Given that the whole purpose of this was just to put the sine of theta in there, the sine of theta is just the sine of 90 degrees, which is just 1. So this doesn't matter at all. It's just the integral of dl. That's the only piece that really matters there. So the magnetic field of the wire then, right at the middle point, is mu naught I over 4 pi A squared. We're really integrating dl. That is over the whole length, so the integral of dl is L. But how long is the wire? Well, the wire is a circle, so it has 2 pi A for its circumference. And we're done. We just got to cancel some things. Pi's cancel, the A's cancel, the 2 comes down there and cancels, and I am left with then mu naught I over 2A. That's it. Now, you may have seen that last year in honors physics. You may have seen that the magnetic field of a wire was mu naught I over 2A. Well, the wire curved into a circle was mu naught I over 2A. But this is where it comes from. And you can probably see why you didn't do it last year, because it's really messy with the Biot-Savart Law. But this is where it comes from. So this was probably the most common thing you would ever be asked. If you were to be asked about the Biot-Savart Law, this is probably the most likely one. But from this, we can actually do some really, really simple ones here. Some simple things that might look bad at first, but once you take a look at them again, you'll say, oh, they're just fractions of the circle. Here's an example of that. Let's say we have a current doing this. And we've got a current coming along here, and the current's just traveling along. same current the whole way, and I have now some radius A, but it's a half a circle. I'd like to know what the magnetic field is right here. And you can apply the Biot-Savart law to this whole situation. But if you think about it for a minute, some of this doesn't matter. And here's why. This current right here points this direction. How does that match up with the radius, this piece right here? Well, they point the same direction or the opposite direction, depending on how you want to look at it. So the cross r hat part means we have a sign of 0, so this part doesn't contribute to the magnetic field. But you probably already knew that if you thought about the right-hand rule. Take your right hand, curl it around like this. It doesn't hit this point. The same thing is true for this side. If I curl my hand, I don't hit that point. So these two sides don't contribute anything to the magnetic field. It's only this curvy part that does. Only the curvy part that curls in, or in this case, it'll be down. The magnetic field will be down. But that's it. That's the only one that'll matter. So how do you find out how big the magnetic field is? Well, you start with the fact that the magnetic field of a wire is mu naught I over 2a for a full circle, but this is not a full circle. It's half of a circle. So I will cut it in half. And then what I would get is the magnetic field is mu naught I over 4a. That's it. Because it's half a circle and these two pieces didn't matter, that's it. Now this could get really messy. If you actually did have these pieces where they mattered or there was something else there, but that is not something that the AP test is likely to give you. It's possible, but it's not very likely. And then we're going to take a look at one last example here. And if you've thought about it for a minute, if you said, gosh, we did the magnetic field of this ring of wire, you probably know what's next. It's a ring, but now we're just up some distance from the middle of the ring. And that's a problem that we've seen in gravity and electric fields, and we've seen it again and again and again. So let's take a look at that one, which has one of the most annoying parts to it with an angle that you're going to see. So here we have it. If you have a ring, radius A, carrying current around like this, and then I'm looking for what the magnetic field is, a distance B, right above the middle. So I want to know what the magnetic field is right here. Now, one thing we're going to need to check at the end, does this match up with our ring from before? Because if it doesn't, then we did something wrong. We do know that this magnetic field should be straight up, because if I curl my hand, it points straight up. I could figure it out from the other ways too. But this is the way that it should point. It should point straight up from here. But let's see if we can figure out what the pieces are of the Biot-Savart law. So the Biot-Savart law again, the integral of mu naught I over 4 pi r squared dl crossed into r hat. There's just a weird piece missing. The piece that's missing comes from the fact of vectors, not the equation here. If I look at this little section dl right here, that little section dl causes a magnetic field by the right-hand rule. Point my thumb in. It causes a magnetic field that comes up like this. If I look at the other side of this, a little piece dl on this side, this piece is going to cause a magnetic field that points over in this direction. So what we can see from this, though, is that if I break these up into components, that this magnetic field and this magnetic field are going to have pieces that cancel. These two are going to cancel. And the piece that I'm left with is going to be this vertical piece here. And I'm going to call this angle right here phi. So even though I've got my base equation here, even though this is going to add a sine of theta, I need to take into account the sine of phi from this whole thing. And that's because you're already considering this to be the sine of theta, a lot of students forget this extra piece right here when they're trying to do a calculation. But other than that, it's really not that bad of a calculation. So let's see what we have as we put it all together. So first of all, the magnetic field. Mu naught is a constant. The current is a constant. 4 pi are constants. They are all coming out. Now, what is the distance from DL to this point? Well, in every situation going around the circle, every single time we would do it, this would be a squared plus b squared. Because that's the distance it'll be. It would be the square root of a squared plus b squared. That's what that really is here. But then we squared it, so now it's a squared plus b squared. Now, this is again where the confusing part can come in. I'm going to skip over here to cross into r hat. This gives us a sine of theta. Now, this gets a little confusing here, but let's go back to this point dl. The question is, what angle does dl, which points into the page, so I'll make it with this marker, and what does it make with the radius? And most people would get confused by this. They would think it's some function here, but if I look, this is the radius, this is dl. They make a 90-degree angle. This is a 90-degree angle that they make. So this right here is really just 1. That's the sine of 90, that's just 1. And that's surprising because we're going to have to find later that there's a sine of phi in here too, but this piece is just 1. Now, what is the sine of phi? Well, if you look at this, you're going to see that there is going to be a little bit of a similar triangle here. This triangle here and this triangle here are similar. And what that means is that this, if this is phi, then that's phi as well. So the sine of phi must be a over the square root of a squared plus b squared. And it's a constant. It stays the same the whole time. And remember, this is not from cross r hat. That's just 1. This is from the component, the vertical component that I need right here. So once we have that, all we need to do is just add in this integral of dl. Well, dl, what is the whole length of this circle? Not this length or anything like that. What is the whole length of the circle? Well, the integral of dl is just L, and that's just 2 pi a. So now you have it. Again, mu naught I, those are constants. 4 pi is a constant. This here is a constant, square root of a squared plus b squared. That's just r squared. The whole length around here was 2 pi a, so we really didn't do an integral. Didn't have to worry about the cross product, again, because that angle was 90. And then the sine of phi is a over the square root of a squared plus b squared. So let's clean this up then. If we clean it up, we're going to see that we get mu naught I, the pi's cancel, the 2 kind of cancels here. We're going to have a squared over 2 a squared plus b squared to the 3 halves. And we've seen that 3 halves denominator thing a lot. So, because this is to a power 1, this is to a power 1/2, so we get 3 halves right there. Let's see if this works though. Let's see if it works for what we had before. And if we reduce this b all the way down to 0, if we reduce that down to 0, then that goes away. We've got a squared to the 3 halves power, which is a cubed, which means it would reduce to mu naught I over 2a. In other words, if b was 0, this thing would reduce down to the magnetic field of a ring at the center, which makes sense. Now, this, again, is probably the second most common thing that they would ever ask you on the AP test. But there you go. Mu naught I a squared over 2 a squared plus b squared to the 3 halves power. One question that students may have is, and you may want to try to prove this yourself, how do you know that phi is the same here and here? And you could actually do triangle stuff. You could, do all the triangle pieces to see how it works out. But I have a different way of doing it. What I do is this. I drop this down. I drop this dot down, and I ask myself, what happens to this angle? And when I drop it down, this angle widens up. When I drop that down, this angle also widens as I go. So they must be the same angle based on the other parameters that are locked in here. I just ask myself what happens with that. But again, you can feel free to prove it to yourself and see if it works. All right, everybody, I hope everybody's staying safe and healthy. And this was our last day of new material. The next couple of days, we'll be working on AP problems, and you can start the progress check. You want to do as well in that as possible. Again, you're trying to learn magnetism. And then look for me to have some things for you after the break where we start electromagnetic induction. Although hopefully we're back in school not long after that. But as always, feel free to email me with questions or concerns or anything like that. And I hope you guys are having a great day. All right, talk to you soon. Bye.